Hi, my dears. In this session, we'll be discussing the revision of all the concepts of the chapter Light, Reflection and Refraction of the Class 10 CBSE Physics. In this table, we will compare the fundamental differences between the light refraction and reflection principles. By definition, refraction is the bending of light ray as it passes from a denser medium to a rarer medium or from a rarer medium to a denser medium. While in reflection, it is the bouncing back of light as the light hits a reflecting surface. The key law that governs the refraction is the Snell's law, which is sin I by sin R is a constant. While in reflection, it is the law of reflection which states the angle of incidence is equal to the angle of reflection. In refraction, as the light enters from one medium to another, there is a change in the speed of light. While in reflection, there is no change in the medium and so there is no change in the speed of light. In refraction, there will be a medium change, and in reflection, as the light hits the reflecting surface, it will be bouncing back into that same medium, and so there is no change in the medium. The fundamental differences between the reflection and the refraction of light. Reflection is the bouncing back of a light ray when it falls on a highly polished surface, while refraction is the bending of a light ray as it travels obliquely from one medium to another. The law of reflection says the incident ray normal to the mirror at the point of incidence and reflected ray all lie on the same plane, while the law of refraction says the incident ray, refracted ray and normal to the interference of two transparent media at the point of incidence all lie on the same plane. Here you see the first law is quite similar in the case of reflection and refraction. The second law of reflection says the angle of incidence I is equal to the angle of reflection R, while in refraction, it is the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant, and that constant is for the light of a given color and a given pair of media. It will be true for all the angle or the incident angle when it is less than 0 or less than 90, which means a light which is falling perpendicular on a refracting surface will not undergo any refraction. So we said sin I by sin R is a constant, which constant is otherwise called as the refractive index. The refractive index is a term that will denote the extent of the bending of light. While refraction is the bending of light ray, the refractive index is the extent of the bending of light ray. So refractive index is denoted as n, and it will be in comparison with the second media with respect to the first media. So refractive index n21 means the refractive index of the second medium with respect to the first medium, and that is equal to the velocity of the first medium divided by the velocity of the second medium. For any given medium, the refractive index of that medium, Nm, is denoted as the speed of light in air, which is called c, divided by the speed of light in that particular medium, which is v. So the refractive index of any particular medium, Nm, is equal to c by v. Here we'll define the terms like Paul, focus, etc. that pertains to the mirror and the lens with this slide. So this is a concave mirror and this is a convex mirror. So let's define the pole of that. Mirror is a reflecting surface. It's a highly polished reflecting surface. And now let's see the define pole. Pole is a geometrical center, or the center of the reflecting surface of the mirror is called the pole. It is denoted by the letter P and it lies on the surface of the mirror. And let's see the aperture. M and N here and M and N here is the aperture of the mirror. So what is the aperture is the diameter of the reflecting surface of the mirror. Now the center of curvature. The reflecting surface, this is the reflecting surface and here this is the reflecting surface. This reflecting surface of the spherical mirror forms a part of the sphere, right, that has a center. So this is a part of the sphere which is like this towards this side, and that sphere will have a center, and that center is known as the center of curvature. Here this portion is a part of the sphere which will be towards this side, and the center of the sphere of which this reflecting surface is a part is called the center of curvature. And now we will define the focus of the focus. Okay, the focus of a concave mirror is the point of convergence where the formed by the reflecting rays that are actually that are incident parallel to the concave mirror. See, when the incident rays, the parallel incident rays fall on a concave mirror, they will converge to this point, and that is the focus. While the parallel rays that fall on a concave mirror will get reflected towards this side, right? But they will appear to diverge. They are diverging, they are not converging, but this diverging point, if you see, they appear to come from a point behind the mirror, and that is the point of divergence, and that point of divergence is the focus, called the focus of the convex mirror. So focus is ultimately the point of convergence or divergence formed by the rays that fall parallelly to the mirror. Then we will discuss the radius of curvature. Radius of curvature is nothing but the distance between C and P. That is, it is the radius of the sphere of which this reflecting surface is a part of. So the distance from C to P is the radius, right, of that bigger sphere. Here also is the distance between C to P, that is the radius. So radius is the radius of the sphere of which the reflecting surface of a spherical mirror forms a part of. And the principal axis. So this is the principal axis, and here also the principal axis. So principal axis will be having the pole and will have the focus and the C all in that single line. So it is a straight line that is passing through the pole, the center of curvature, and the principal focus. And principal axis is normal to the mirror at its pole. Okay, so you can see this. That's why, because it's a normal, the reflecting it will be like the normal at the pole, the reflecting ray will be reflected in the same direction. Okay, so the incident ray and reflection, there will not be any angle because angle of incidence is 0 here. Okay, so and then what is okay, now we'll define focal length. Focal length is the distance between F and P. So here also P and F, this is the focal length, that is the distance between the principal focus and the pole of the mirror is the focus focal length. Okay, it is denoted by the letter F. For spherical mirrors of smaller aperture, the radius of curvature, that is R, that is the distance between C and P, is normally twice the focal length. Okay, so that is in this chapter we'll be discussing only those mirrors that have smaller apertures. So you can always take the formula for R as twice the focal length. And now we'll define the terms pertaining to the lenses. So what is lens? It is a transparent material which is bound by two spherical surfaces. So here it is this is a spherical surface, and here this is the spherical surface. So either one or both the surfaces are spherical. At least it should be like that. At least it can be either one surface is plane and the other surface is spherical, or both the surfaces are spherical, and that is called lenses. Then in concave lens or double concave lens, both the center is curved inwards. In the case of a convex lens or double convex lens, that is, both the reflecting surfaces are convex lens. So the center will be bulged outwards. And now we'll see the optical center. See, O is the optical center. It is the central point of a lens. And here, the ray of the light that pass through the optical center will pass without any deviation as it passes through the optical center. So this ray will not have any deviation. See, it is going straight. Here also, if you see, this ray is going straight. Why it is going straight? It is passing through the optical center. And why? There is no angle here. There is this angle, it's zero. There is no diffraction that will happen here, because any refraction, for refraction to occur, the light should fall obliquely. At the point of O, it is perpendicular. So the angle is zero. So it will not suffer any deviation. It will go straight. Then the aperture of the lens. Aperture of the lens is this effective diameter, this Mn, and here also this portion to this portion. Mn is the aperture or it is effective diameter of this circular outline of this spherical lens. Okay. And then let's see the center of curvature. Center of curvature is the center of these two spherical surfaces. In this spherical surface, we'll have this as a center, and this spherical surface will have somewhere here as a center. So that is the center of these two of the sphere of which the lens is a part of. And in the case of lens, here also we will be discussing lenses that are of smaller apertures. So here also C will be twice the focal length. Here, instead of C, in the case of lenses, instead of C, we will define it as 2f1. Why f1? This lens, okay, this lens will have the focus, the f1 here, right? And the other convex, sorry, this one will have towards here and this one will have towards here. So it is 2f1 means twice this focal, twice 2f1 is the center of curvature is twice the focal length, and C is denoted as twice the 2f1 because it belongs to the first part of the lens, and f2 from here it will be written f2 is the second focal focus and the second focal the second center of curvature, and so this will be 2f2. Okay, as this is two spherical surfaces, that's why f1 and f2. Here also 2f1, f1, that is 2f1 is the center of curvature, and f2 and f2 will come here. But in see, in ray optics, we always have the light falling from the left hand side, and even the numbering should be from the left hand side. That is why the first lens is denoted as 2f1 and the f2 at f1 here, and towards this side it will be f2 and 2f2. Then anything else? Yeah, we will define the focal length. Oh, principal axis we discussed, and now the focus. Focus. So the focus is this point of convergence in the case of a convex lens, and in the case of a concave lens, it is the point of divergence. It is from here it will diverge, right? So it is formed by the refracted rays when the parallel incident rays fall on the lenses. So this parallel incident rays will undergo refraction and will converge in the case of a concave lens, and this point of convergence is the focus here. And this point, these rays will hit the concave lens, will diverge, and they will appear to come from these diverging rays when we extend, or it will appear to come from a point on the principal axis, and that point is the focus in the case of a concave lens. And the focal length is the distance between the optical center and the focus. Okay, and that is denoted as small f. In optics, be it reflection or refraction, or be it in the case of mirror or it in the case of lens, we keep the object always on the left hand side, or we consider the light rays should be falling on the mirror or the lens from the left hand side. Real images are always inverted and virtual images are always erect. Whether it is a mirror or a lens, these three are the same. In the case of a mirror, The real images are on the formed in front of the mirror, or it is on the same side of the object. But in the case of a lens, it is a refraction, right? So the light ray will pass through the lens. So, and it will, the image will be formed behind the lens or on the other side of the lens. In the case of a mirror, the virtual images are formed behind the mirror, as it is a reflecting surface. In the case of the lens, the virtual images are formed on the same side as the lens or same side as the object. Now we will see the behavior of the light ray that will fall parallel to the principal axis in the case of the concave and the convex mirror and the convex and the concave lens. In the case of a concave mirror, the parallel ray that hits the concave mirror the incident ray will make I, the incident angle of incidence with the normal. It will trace the same angle of reflection, and it will be and this will get reflected like this, and it will be passing through the focus. In the case of a convex lens, the parallel ray hits this point, makes the same the angle of incidence as the angle of reflection. It will get reflected by it, or it will get diverged away, and this this will be emerging from this particular point. This is the point of divergence, and that is the focus, and that is on the principal axis. In the case of the convex lens, the light ray that is parallel falls on the lens, will undergo refraction and will converge to a point on the principal axis called the focus. And here also the parallel ray will get diverged after refraction, but this point, this diverging ray will appear to come from this particular point called focus on the principal axis. So be it the concave mirror or convex mirror or convex lens or a concave lens, the light ray that fall parallel to the principal axis after reflection or refraction will be passing through the focus. So any parallel ray parallel to the principal axis in all these cases will be passing through the focus. The light ray that pass through the focus in the case of a concave mirror is following the law of reflection. It will make the same I is equal to R and is emergent rays parallel to the principal axis. In the case of a convex mirror, this is the incident ray. It is making I with the normal, and it is making the same I is equal to R following the law of reflection. It is making the same angle of incidence with the angle of as the angle of reflection, and it is emerging parallel to the principal axis. A convex lens, the ray that is passing through the focus and falling obliquely into the convex lens is getting refracted and emerging parallel to this principal axis. The concave lens, this incident ray is directed towards the focus and it is getting refracted, and this emergent ray is parallel to the principal axis. So be it a concave mirror, convex mirror, or the lens, or any lens, convex or concave lens, the ray that is passing through the focus or falling obliquely into this reflecting surface through the focus will be emerging parallel to the principal axis. The ray that passes through the center of curvature C is reflected through the tracing the same path just as the incident ray. See this concave mirror. The incident ray falls like this through the center of curvature. The reflected ray is also tracing the same path. That's why we give this arrow. See, in the case of a convex mirror, the incident ray is directed towards the center of curvature. Is this reflecting the ray is tracing the same path just as the incident ray. So here in the case of the lens, just remember that the ray that passes through the optic center and not the center of curvature, okay? The ray that passes through the optic center will not be having any deviation. So The ray that is directed towards the geometrical center of the concave mirror and a convex mirror. See, this incident ray that is incident on the at the pole of the concave mirror is making angle I with the principal axis. See, at the pole, the principal axis, when the ray is obliquely falling at the pole, the normal at the pole will be the same principal axis. It will trace the same angle of reflection as I, and so it will follow the law of reflection, that is I equal to R, and it will be reflected obliquely. Here also this incident ray at the pole in the convex mirror is also making the angle of reflection and is reflected obliquely. So in the case of a concave mirror and a convex mirror, at the geometrical center, the incident, that is at the pole, the incident ray which is directed towards the pole will be reflected obliquely following the law of reflection, which is angle of incidence is equal to the angle of reflection. And now in the case of the geometrical center of the lenses, the geometrical center of the lenses is the optical center or O of the lens. Here, the light ray that passes through the optical center will not suffer any deviation, and it will be going in a same straight line path, and it will not have any bending. See, in both the cases, this light ray is not suffering any deviation in its path. Why? At the point O, it is making a 90 degree. So, when the light, for refraction to occur, the light has to fall obliquely. Here at the point O, the angle is 90 degrees Celsius, which makes so the refraction does not happen and the light ray will not suffer any deviation, and that's why it will be tracing the, it will be following, it will not suffer any refraction. We'll be discussing the image formation, comparing the concave mirror and the convex lens. See, in concave mirror and convex lens, the image formation positions are quite comparable, and that is why, and we'll have to see that in the case of a mirror, the images, real images are formed in front of the mirror, while in the case of the lens, real images are formed on the other side of the lens. See, in the case of a concave mirror, at the point when the object is at infinity, the parallel rays will make the image at the focus. We have explained this in our descriptive classes. So as is the revision, I will not be explaining them. If in case you wanted description, please go to the playlist. So the parallel rays will converge and form the image at the focus at F. So here, in the case of a convex lens, the parallel rays that hit the convex lens will undergo refraction and will be converging and forming the image at the point F2 or at the focus. So in both the cases, the image is formed at the focus. Because see, in both the cases, they are real images. Here in the mirror, it is a real and inverted image. Here also, it's a real and inverted image. In the case of a mirror, the real images are formed in front of the mirror, and here the real image is formed on the other side of the mirror. At the focus, the size of the image is a very small and point-sized image is formed. When the object is beyond C, the center of curvature, the image is formed in between C and F. Here, if you see, the object is placed beyond the 2F1 or the C1. So here also, if you see, the image is formed in between C and F. The image is formed in front of the mirror as it is a real and inverted image. Here also it's a real and inverted image, but it is formed on the other side of the lens. The image is a small image as compared to the object, and here also it's a small image as compared to the object. So we discussed earlier itself that when the object is at infinity and beyond C, the image size will be smaller than the object. And now we will go to the next position when the object is placed at C or at 2f1. In the case of a concave mirror, when the object is placed at C, the image is also formed at C. The image is a real and inverted image and it is formed in front of the mirror. It is of the same size. Here, in the case of a convex lens, when the object is placed at C1 or 2f1, the image is formed also at the center of curvature, which is the second center of curvature, which is C2 or 2f2, and it is a real and inverted image. It's on the other side of the lens and it is of the same size. The image is of the same size as the object. So in both the cases, remember at the center of curvature, in the case of a concave mirror and the convex lens, at the position when the object is placed at C, the image is also formed at C and is of the same size. And in both the cases, the images are real and inverted. When the object is placed between C and F. So when the object is placed in between C and F, the image is formed beyond C. It is a real and inverted image, and it is in front of the mirror, and it is an enlarged image in the case of a concave mirror. In the case of a convex lens, when the object is placed in between CF1 or 2F1 and F1, the image is formed beyond C2 or 2F2 and it is an enlarged image. So you can see the similarity. The only difference here is the real and inverted images are formed on the other side of the lens, while the real and inverted images are formed on the same side of the mirror. And both the images are inverted, real and inverted, and also it's enlarged. And then when the object is at F. At F, the image is formed at infinity. In both the cases, the images is formed at infinity, be it concave mirror or the convex lens. The image is a real and inverted image. Here it is formed in front of the mirror and here it is formed on the other side of the lens. The image is a really highly enlarged image. As we discussed earlier, when the object is placed at infinity, the image is formed at F. And when the object is placed at F, the image is formed at infinity. Please remember, when the object is at infinity and beyond C, the image formed is a diminished image. At C, the image formed is of the same size, and past C to P, the images formed are enlarged. Past to F1 to O, the images formed are whenever the object is placed after 2f1. At 2f1, it is of the same size. That is, at C1, it is of the same size. Image is formed of the same size. Beyond 2f1 and in between the optic center, or anywhere between the optic center and beyond 2f1, the image formed is an enlarged image. Now the image formation by a convex mirror and a concave lens. When the object is placed at infinity, we know the image is formed at the principal focus. Here also the object is placed at infinity means the image is formed at principal focus. So whatever, be it any mirror or any lens, whenever the object is at infinity, the image is formed at the focus. Then here the image is formed behind the mirror. In the case of a concave lens, it is a virtual image, so it is formed in front of the mirror. So always remember, virtual images are always erect. So this is a virtual and erect image. It is formed behind the mirror in the case of a convex mirror, and in the case of a concave lens, it is a virtual and erect image formed in front of the lens, and it is a highly diminished image is formed at the focus. Whenever the image is formed at the focus, the image size is a very highly diminished size. when the object is at a finite distance from the convex mirror and the concave lens. When the object is at any finite distance from that is it is at a finite distance from the mirror or from the pole of the mirror or from the optic center of the lens, the image is formed between the pole and the focus. Here the image is formed in between the optic center and the focus. So in both the cases, it's a virtual and erect image. Here the virtual image is formed behind the mirror. In concave lens, the virtual image is formed in front of the lens. The image formed is a diminished or small image in both the cases. And now we will see the formulas in the mirror and the lens. In the mirror formula is 1 by f is equal to 1 by v plus 1 by u, while the lens formula is 1 by f is equal to 1 by v minus 1 by u. So as you know, f is the focal length, v is the image distance, and u is the object distance. Remember, mirror is more and you have the plus here, and lens it is less and it is minus here. The mirror formula is valid for all the spherical mirrors in all the situations and at all positions of the object. Likewise, the lens formula is also valid in all the situations for all spherical lenses and at all positions. Remember to apply the Cartesian sign conventions whenever you are having any numericals. Here we are discussing mirror and lens of smaller apertures. So your radius of curvature is twice the focal length, and in the case of the lenses, you have your C, the center of curvature, as twice the focal length. The magnification is the height of the image divided by height of the object. But in the case of the mirror, the equation will be minus V by U, and in the case of the lenses, it will be just V by U. And in lens, we also have the formula for power of to find the power of the lens, and power is 1 divided by the focal length of the lens. And the unit of power is diopters. In diopter, the focal length should always be in meters. And now this is the Cartesian sign convention. Remember like this. This is the x-axis and this is your y-axis, and the point P will be your the middle point O of the x and y axis. Anywhere from P to the positive x-axis will be your any measurements taken from the pole towards this side. Towards the right hand side will be positive. Any measurements taken above the principal axis will also be positive. Below the principal axis, that is below the point pole, will be negative, and it will be just as the positive x and the y axis. Please follow the Cartesian sign conventions for all your numericals. Likewise, in the lenses, it is just the same. Or any measurements towards the positive x-axis and positive y-axis will be positive, and any measurements towards the negative y and the negative x-axis will be negative. And remember, the focal length of the concave lens is always negative and the convex lens is always positive, because here the image is the f2 is this is the focal length. So here is a f coming, so it is positive, and here f is towards this side, and so it is negative. The whole formulas from the light, we have already discussed this one. So here I just want to see u will always be negative as it is in the left hand side of the x-axis, and h is above the principal axis, so it will always be positive. And remember, the focal length of a concave mirror and also the concave lens, both will be negative, and focus length or f of the convex mirror and convex lens, both will be always positive. Then we discussed this. The N21, the refractive index of the medium will be of second medium in respect the N21. The refractive index of the second medium with respect to the first medium will be the speed of light in the medium 1 divided by the speed of light in medium 2, that is V1 by V2. The image formation by the plane mirror. Remember, the plane mirror we already discussed. It's a virtual and direct image. The size of the image and the size of the object is equal. The image is a laterally inverted image. Remember, B will be appearing as D. Image is far behind the mirror, just as the object is in front of the mirror. That is, the U is equal to 30. That is the image distance from the image to the pole. The center of the mirror will be 30 centimeter, means the image distance will also be 30 centimeter. In this slide, I want to discuss the image formation by the two spherical mirrors and the two lenses. Please do not draw this picture anywhere in your exam paper, as this is just a memory trick to recollect the concept that you already studied. But if you are able to recollect without this, kindly skip this. If not, continue. Here, the object is shown in blue color arrow. The virtual images are shown in green color arrow. The real images are shown in orange color arrow. See, in all the cases, when the object is placed at infinity, the image is formed at focus. So you have this concept very clear. Whenever the object is in infinity, the image is formed at focus. Now, the object positions I am marking as 1, 2, 3, 4, 5, 6, and the image positions I am marking as 1 prime, 2 prime, and goes on. Now we will see the concave mirror. So the first position is at infinity. So the object is placed at infinity. So when the object is at infinity, your f is formed, the image is formed at f. So that is your 1 prime. That is when the object is at infinity, the image is at focus. So have this concept very clear. And the second, so everywhere in this image, you remember all your 1 will be infinity. So the object is at infinity, you have your image at focus, and that is your first image, that is 1 prime. When the object is placed in between, that is beyond C, that is a second position. So the image is formed in between C and F in the case of a concave mirror. It is a real and inverted image, and it is a small image. So by this figure, this one is a large one and this is a small one. So see, at the focus it's a diminished image, so you got a very small real inverted image. At the second position, that is beyond C, you got a diminished image, but still it is real and it is inverted. Then the third position is at C. So at C, I said the image size and the object size is the same. So you find this quite similar, and it is real and inverted here. The fourth position is in between C and F. So where is your 4? Here. So when you start your 1, 2, 3, 4, 5 like this, your 1 prime, 2 prime will be like this. It's like a V, but like a greater than symbol. Okay, that's what you should remember. The fourth position, and this is beyond C, is the fourth position, fourth image. The fifth position is at F, and remember, when the object is at infinity, the image is at F, and when the object is at F, the image is at infinity. So 5 prime is your infinity position. Okay, so the image is already formed at infinity. So now you have your object placed in between F and P. Beyond infinity, there is nothing, right? So you put that, where will you put? You will put it as a virtual image behind the mirror. Okay, so you can't go beyond infinity, so your sixth position is behind the mirror. So with this one single picture, you will be able to recollect and summarize all the image positions. I said a V because, or the concave has got the V here, and this is like a greater than symbol, which is just like the the concave mirror. See, this object at infinity is a very large object. Here at the joining point of this V, here you have the focus. At the focus, you have a very small or a diminished image. And as you go from here, this picture will even make you recollect the size of the images. See, here, this is a small, from the, always the image is formed from the principal axis. So here if you see, it is a small image. So by this you will see here the 2 is a quite bigger one. So you can say immediately say this is diminished. Here it looks quite similar, right? So 3 and 3 prime are of the same size. That is at C, the object size and the image size is same. Then 4, at the position 4, it is between C and F. See this one, this size and this size. This is much bigger size. So you can say this is an enlarged one. At 5, at the position F, you know the image is formed at infinity. Remember this at infinity, image at F, and at F, the image is at infinity. The 6th position is in between F and P. So you already crossed infinity. So you have to make a virtual image, and that's where you make the virtual image. So, and here we'll go for the convex lens. This is just the same as this. At the first position is infinity. You have your first point as at F. So when you start your convex lens or anywhere, your first image will always be at F. So it's a real inverted image, but on the other side of the lens, and it is it's real and inverted, and it says diminished image. The second position of the image object is in beyond 2f1 or beyond c1. Okay, it's beyond the center of curvature. So you get the image in between f2 and 2f2. See, your third position is C. At center of curvature, you know, the image is also at center of curvature, same size. So where will 2 come? 2 will come in between the infinity and the 2f1. So it is beyond 2f1. So here also, the object will be between f2 and 2f2. Where will the image come? Here. Okay. Then the fourth position will be in between 2f1 and f1. So that is the fourth position. See, if you see here, it is going to be a longer image. It's a bigger image. So it's a real, inverted, and a bigger or larger enlarged image. The sixth position, okay, by the fifth position is at focus. At focus, you anyway know it is at infinity. So this is a infinity. It will make a enlarged image. So at infinity, you got the enlarged image. So now beyond F to beyond F, that is in between F1 and O, you have a you crossed anyway infinity, so you have to make a virtual image, and so virtual images of the lens will be on the same side, and so you will show an enlarged image on the left hand side of the lens, and it is an enlarged image. It will be formed beyond 2f1 as it will be an enlarged image. So in concave mirror and convex lens, whenever the object is beyond infinity, in between, that is beyond, that is infinity and in between infinity and the center of curvature, or infinity and 2f1, the image formed is a diminished image. At C, it is of the same size. Okay, at 2f1c, it's of the same size. And any points between after beyond C, that is after in between the center of curvature and the P, or 2f1 and the O, it is going to be an enlarged image. Okay, and this is a convex mirror. The first position is infinity, so you know your the image. And see, in convex mirror, it is always, it will be forming a virtual and erect image. So it is, see, virtual, it is erect, and that's why I put the green color. So 1 prime is at the focus. Second one, anywhere at a finite distance from the mirror is your second position where you keep the object. So your image is formed anywhere between the pole and the focus, and it is a diminished image. This is a concave lens. The first position is at infinity, so you know your image is at the focus. The second position is anywhere at a finite distance from the lens, so you put it here. So the image will be formed further away from the focus, in between the focus and the optic center. And so you put it here. It is a, by this you can see it's a diminished image. Another analogy I want to say is it's a concave. I said the greater than sign, or a, uh, lateral V. Here also this is a concave lens, and here also you can make out a V. So by the V, we will be able to find out the size of the object also. Okay. And the convex mirror, you will have to take the slanting line of the X. Here you draw a line like this, and here from F you should draw the line. Here don't draw the line here. It is better you start your line from F downwards. So you will get your X as the slanting line of the X, and that necessarily that will help you to remember all the positions of the image formation from all the mirror and the lens. I want to conclude that please do not refer to this or draw this images anywhere in your exam papers, but this is for you to memorize and recollect the concepts. So thank you, dears, for your attention and study well. If you like this session, in your YouTube, you may subscribe or like this presentation. And thank you again.